Building automation is the automatic centralized control of a building's heating, ventilation and air conditioning, lighting and other systems through a building management system or building automation system. The objectives of building automation are improved occupant comfort, efficient operation of building systems, and reduction in energy consumption and operating costs. Building automation is an example of a distributed control system, the computer networking of electronic devices designed to monitor and control the mechanical, security, fire and flood safety, lighting, HVAC and humidity control and ventilation systems in a building. BAS core functionality keeps building climate within a specified range, provides light to rooms based on an occupancy schedule, monitors performance and device failures in all systems, and provides malfunction alarms to building maintenance staff. A BAS should reduce building energy and maintenance costs compared to a non-controlled building. Most commercial, institutional, and industrial buildings built after 2000 include a BAS. Many older buildings have been retrofitted with a new BAS, typically financed through energy and insurance savings, and other savings associated with preemptive maintenance and fault detection. A building controlled by a BAS is often referred to as an intelligent building, smart building, or a smart home. Commercial and industrial buildings have historically relied on robust proven protocols while proprietary and poorly integrated purpose-specific protocols were used in homes. Recent IEEE standards and consortia efforts like Envoy or Civicon have provided a standards-based foundation for heterogeneous networking of many devices on many physical networks for diverse purposes, and quality of service and failover guarantees appropriate to support human health and safety. Accordingly, commercial, industrial, military and other institutional users now use systems that differ from home systems mostly in scale. See Home Automation for more on entry-level systems, Envoy, 1905.1, and the major proprietary vendors who implement or resist this trend to standards integration. Almost all multi-story green buildings are designed to accommodate a BAS for the energy, air and water conservation characteristics. Electrical device demand response is a typical function of a BAS, as is the more sophisticated ventilation and humidity monitoring required of tight insulated buildings. Most green buildings also use as many low-power DC devices as possible, typically integrated with power over Ethernet wiring, so by definition always accessible to a BAS through the Ethernet connectivity. Even a passive house design intended to consume no net energy whatsoever will typically require a BAS to manage heat capture, shading and venting, and scheduling device use. Automation system. The term building automation system, loosely used, refers to any electrical control system that is used to control a building's heating, ventilation and air conditioning system. Modern BAS can also control indoor and outdoor lighting as well as security, fire alarms, and basically everything else that is electrical in the building. Old HVAC control systems, such as 24 VDC-wired thermostats or pneumatic controls, are a form of automation but lack the modern system's flexibility and integration. Buses and protocols. Most building automation networks consist of a primary and secondary bus which connect high-level controllers with lower-level controllers, input-output devices and a user interface. ASHRAE's Open Protocol BACnet or the Open Protocol on Talk specified how most such devices interoperate. Modern systems use SNMP to track events, building on decades of history with SNMP-based protocols in the computer networking world. Physical connectivity between devices was historically provided by dedicated optical fiber, Ethernet, ARCNET, RS-232. RS-485 or a low-bandwidth special-purpose wireless network. Modern systems rely on standards-based multi-protocol heterogeneous networking such as that specified in the IEEE 1905.1 standard and verified by the Envoy auditing mark. These accommodate typically only IP-based networking but can make use of any existing wiring, and also integrate powerline networking over AC circuits, power over Ethernet low-power DC circuits, High-bandwidth wireless networks such as LTE and IEEE 802.11n and IEEE 802.11ac and often integrate these using the building-specific wireless mesh open standard ZigBee. Proprietary hardware dominates the controller market. Each company has controllers for specific applications. Some are designed with limited controls and no interoperability, such as simple packaged rooftop units for HVAC. Software will typically not integrate well with packages from other vendors. Cooperation is at the ZigBee LAN talk level only. Current systems provide interoperability at the application level, allowing users to mix and match devices from different manufacturers, and to provide integration with other compatible building control systems. These typically rely on SNMP, long used for this same purpose to integrate diverse computer networking devices into one coherent network. Types of inputs and outputs. Analog inputs are used to read a variable measurement. Examples are temperature, humidity and pressure sensors, which could be thermistor, 4 to 20 mA, 0 to 10 volt, or platinum resistance thermometer, or wireless sensors. A digital input indicates if a device is turned on or not. Some examples of an inherently digital input would be a 24 VDC AC signal, current switch, an airflow switch, or a volta-free relay contact. Digital inputs could also be pulse-type inputs counting the frequency of pulses over a given period of time. An example is a turbine flow meter transmitting rotation data as a frequency of pulses to an input. Analog outputs control the speed or position of a device, such as a variable frequency drive, an IP transducer, or a valve or damper actuator. An example is a hot water valve opening up 25% to maintain a set point. Another example is a variable frequency drive ramping up a motor slowly to avoid a hard start. Digital outputs are used to open and close relays and switches as well as drive a load upon command. An example would be to turn on the parking lot lights when a photocell indicates it is dark outside. Another example would be to open a valve by allowing 24 VDC AC to pass through the output powering the valve. Digital outputs could also be pulse-type outputs emitting a frequency of pulses over a given period of time. An example is an energy meter calculating kilowatt-hour and emitting a frequency of pulses accordingly. Infrastructure controllers are essentially small, purpose-built computers with input and output capabilities. These controllers come in a range of sizes and capabilities to control devices commonly found in buildings, and to control sub-networks of controllers. Inputs allow a controller to read temperatures, humidity, pressure, current flow, airflow, and other essential factors. The outputs allow the controller to send command and control signals to slave devices, and to other parts of the system. Inputs and outputs can be either digital or analog. Digital outputs are also sometimes called discrete depending on manufacturer. Controllers used for building automation can be grouped in three categories: programmable logic controllers, system network controllers, and terminal unit controllers. However, an additional device can also exist in order to integrate third-party systems into a central building automation system. Terminal unit controllers usually are suited for control of lighting and/or simpler devices such as a packaged rooftop unit, heat pump, VAV box, or fan coil, etc. The installer typically selects one of the available pre-programmed personalities best suited to the device to be controlled, and does not have to create new control logic. Occupancy Occupancy is one of two or more operating modes for a building automation system. Unoccupied, morning warm-up, and nighttime setback are other common modes. Occupancy is usually based on time of day schedules. In occupancy mode, the BAS aims to provide a comfortable climate and adequate lighting, often with zone-based controls so that users on one side of a building have a different thermostat than users on the opposite side. A temperature sensor in the zone provides feedback to the controller, so it can deliver heating or cooling as needed. If enabled, morning warm-up mode occurs prior to occupancy. During morning warm-up, the BAS tries to bring the building to set point just in time for occupancy. The BAS often factors in outdoor conditions and historical experience to optimize MWU. This is also referred to as optimized start. An override is a manually initiated command to the BAS. For example, many wall-mounted temperature sensors will have a push button that forces the system into occupancy mode for a set number of minutes. Where present, web interfaces allow users to remotely initiate an override on the BAS. Some buildings rely on occupancy sensors to activate lighting and/or climate conditioning. Given the potential for long lead times before a space becomes sufficiently cool or warm, climate conditioning is not often initiated directly by an occupancy sensor. Lighting can be turned on, off, or dimmed with a building automation or lighting control system based on time of day, or on occupancy sensor, photosensors and timers. One typical example is to turn the lights in a space on for a half hour since the last motion was sensed. A photocell placed outside a building can sense darkness, and the time of day, and modulate lights in outer offices and the parking lot. Lighting is also a good candidate for demand response, with many control systems providing the ability to dim lights to take advantage of drive incentives and savings. In newer buildings, the lighting control is based on the field bus DALI. Lamps with DALI ballasts are fully dimmable. DALI can also detect lamp and ballast failures on DALI luminaires and signals failures. Air handlers Most air handlers mix return and outside air, so less temperature humidity conditioning is needed. This can save money by using less chilled or heated water. Some external air is needed to keep the building's air healthy. To optimize energy efficiency while maintaining healthy indoor air quality, demand control ventilation adjusts the amount of outside air based on measured levels of occupancy. Analog or digital temperature sensors may be placed in the space or room, the return and supply air ducts, and sometimes the external air. Actuators are placed on the hot and chilled water valves, the outside air and return air dampers. The supply fan is started and stopped based on either time of day, temperatures, building pressures or a combination. Constant volume air handling units. The less efficient type of air handler is a constant volume air handling unit, or CAV. The fans in CAVs do not have variable speed controls. Instead, CAVs open and close dampers and water supply valves to maintain temperatures in the building's spaces. They heat or cool the spaces by opening or closing chilled or hot water valves that feed their internal heat exchangers. Generally, one CAV serves several spaces. Variable volume air handling units. A more efficient unit is a variable air volume air handling unit, or VAV. VAVs supply pressurized air to VAV boxes, usually one box per room or area. A VAV air handler can change the pressure to the VAV boxes by changing the speed of a fan or blower with a variable frequency drive, or by moving inlet guide vanes to a fixed speed fan. The amount of air is determined by the needs of the spaces served by the VAV boxes. Each VAV box supply air to a small space, like an office. Each box has a damper that is opened or closed based on how much heating or cooling is required in its space. The more boxes are open, the more air is required, and a greater amount of air is supplied by the VAV air handling unit. Some VAV boxes also have hot water valves and an internal heat exchanger. The valves for hot and cold water are opened or closed based on the heat demand for the spaces it is supplying. These heated VAV boxes are sometimes used on the perimeter only, and the interior zones are cooling only. A minimum and maximum CFM must be set on VAV boxes to assure adequate ventilation and proper air balance. VAV hybrid systems. Another variation is a hybrid between VAV and CAV systems. In this system, the interior zones operate as in a VAV system. The outer zones differ in that the heating is supplied by a heating fan in a central location, usually with a heating coil fed by the building boiler. The heated air is ducted to the exterior dual duct mixing boxes and dampers controlled by the zone thermostat, calling for either cooled or heated air as needed. Central plant. A central plant is needed to supply the air handling units with water. It may supply a chilled water system, hot water system and a condenser water system, as well as transformers and auxiliary power unit for emergency power. If well managed, these can often help each other. For example, some plants generate electric power at periods with peak demand, using a gas turbine, and then use the turbine's hot exhaust to heat water or power an absorptive chiller. Chilled water system. Chilled water is often used to cool a building's air and equipment. The chilled water system will have chiller, and pumps. Analog temperature sensors measure the chilled water supply and return lines. The chiller, are sequenced on and off to chill the chilled water supply. A chiller is a refrigeration unit designed to produce cool water for space cooling purposes. The chilled water is then circulated to one or more cooling coils located in air handling units, fan coils, or induction units. Chilled water distribution is not constrained by the 100-foot separation limit that applies to DX systems, thus chilled water-based cooling systems are typically used in larger buildings. Capacity control in a chilled water system is usually achieved through modulation of water flow through the coils. Thus, multiple coils may be served from a single chiller without compromising control of any individual unit. Chillers may operate on either the vapor compression principle or the absorption principle. Vapor compression chillers may utilize reciprocating, centrifugal, screw, or rotary compressor configurations. Reciprocating chillers are commonly used for capacities below 200 tons. Centrifugal chillers are normally used to provide higher capacities. Rotary and screw chillers are less commonly used, but are not rare. Heat rejection from a chiller may be by way of an air-cooled condenser or a cooling tower. Vapor compression chillers may be bundled with an air-cooled condenser to provide a packaged chiller, which would be installed outside of the building envelope. Vapor compression chillers may also be designed to be installed separate from the condensing unit. Normally such a chiller would be installed in an enclosed central plant space. Absorption chillers are designed to be installed separate from the condensing unit. Condenser water system, cooling tower, and pumps are used to supply cool condenser water to the chillers. Because the condenser water supply to the chillers has to be constant, variable speed drives are commonly used on the cooling tower fans to control temperature. Proper cooling tower temperature assures the proper refrigerant head pressure in the chiller. The cooling tower set point used depends upon the refrigerant being used. Analog temperature sensors measure the condenser water supply and return lines. Hot water system. The hot water system supplies heat to the building's air handling unit or VAV box heating coils, along with the domestic hot water heating coils. The hot water system will have a boiler, and pumps. Analog temperature sensors are placed in the hot water supply and return lines. Some type of mixing valve is usually used to control the heating water loop temperature. The boiler, and pumps are sequenced on and off to maintain supply. The installation and integration of variable frequency drives can lower the energy consumption of the building's circulation pumps to about 15% of what they had been using before. If that sounds hard to believe, I'll explain, and we can do the math. A variable frequency drive functions by modulating the frequency of the electricity provided to the motor that it powers. In the USA, the electrical grid uses a frequency of 60 Hz or 60 cycles per second. Variable frequency drives are able to decrease the output and energy consumption of motors by lowering the frequency of the electricity provided to the motor. However, the relationship between motor output and energy consumption is not a linear one. If the variable frequency drive provides electricity to the motor at 30 Hz, the output of the motor will be 50% because 30 Hz divided by 60 Hz is 0.5 or 50%. The energy consumption of a motor running at 50% or 30 Hz will not be 50%, but will instead be something like 18% because the relationship between motor output and energy consumption are not linear. The exact ratios of motor output or Hertz provided to the motor, and the actual energy consumption of the variable frequency drive/motor combination depend on the efficiency of the variable frequency drive. For example, because the variable frequency drive needs power itself to communicate with the building automation system, run its cooling fan, etc. If the motor always ran at 100% with the variable frequency drive installed, the cost of operation or electricity consumption would actually go up with the new variable frequency drive installed. The amount of energy that variable frequency drives consume is nominal and is hardly worth consideration when calculating savings. However, it did need to be noted that VFDs do consume energy themselves. Due to the fact that the variable frequency drives rarely ever run at 100% and spend most of their time in the 40% output range, and the fact that now the pumps completely shut down when not needed, the variable frequency drives have reduced the energy consumption of the pumps to around 15% of what they had been using before. Alarms and security. All modern building automation systems have alarm capabilities. It does little good to detect a potentially hazardous or costly situation if no one who can solve the problem is notified. Notification can be through a computer, pager, cellular phone voice call, audible alarm, or all of these. For insurance and liability purposes, all systems keep logs of who was notified, when and how. Alarms may immediately notify someone or only notify when alarms build to some threshold of seriousness or urgency. At sites with several buildings, momentary power failures can cause hundreds or thousands of alarms from equipment that has shut down. These should be suppressed and recognized as symptoms of a larger failure. Some sites are programmed so that critical alarms are automatically resent at varying intervals. For example, a repeating critical alarm might resound at 10 minutes, 30 minutes, and every 2 to 4 hours thereafter until the alarms are resolved. Common temperature alarms are space, supply air, chilled water supply, hot water supply. Pressure, humidity, biological and chemical sensors can determine if ventilation systems have failed mechanically or become infected with contaminants that affect human health. Differential pressure switches can be placed on a filter to determine if it is dirty or otherwise not performing. Status alarms are common. If a mechanical device like a pump is requested to start, and the status input indicates it is off, this can indicate a mechanical failure. Or, worse, an electrical fault that could represent a fire or shock hazard. Some valve actuators have end switches to indicate if the valve has opened or not. Carbon monoxide and carbon dioxide sensors can tell if concentration of these in the air are too high, either due to fire or ventilation problems in garages or near roads. Refrigerant sensors can be used to indicate a possible refrigerant leak. Current sensors can be used to detect low current conditions caused by slipping fan belts, clogging strainers at pumps, or other problems. Security systems can be interlocked to a building automation system. If occupancy sensors are present, they can also be used as burglar alarms. Because security systems are often deliberately sabotaged, at least some detectors or cameras should have battery backup and wireless connectivity and the ability to trigger alarms when disconnected. Modern systems typically use power over Ethernet, which is capable of charging such batteries and keeps wireless networks free for genuinely wireless applications, such as backup communication in outage. Fire alarm panels and their related smoke alarm systems are usually hardwired to override building automation. For example, if the smoke alarm is activated, all the outside air dampers close to prevent air coming into the building, and an exhaust system can isolate the blaze. Similarly, electrical fault detection systems can turn entire circuits off, regardless of the number of alarms this triggers or persons this distresses. Fossil fuel combustion devices also tend to have their own overrides, such as natural gas feed lines that turn off when slow pressure drops are detected, or when excess methane is detected in the building's air supply. Good BAS are aware of these overrides and recognize complex failure conditions. They do not send excessive alerts, nor do they waste precious backup power on trying to turn back on devices that these safety overrides have turned off. A poor BAS, almost by definition, sends out one alarm for every alert, and does not recognize any manual, fire or electric or fuel safety override. Accordingly, good BAS are often built on safety and fire systems. Room automation. Room automation is a subset of building automation and with a similar purpose, It is the consolidation of one or more systems under centralized control, though in this case in one room. The most common example of room automation is corporate boardroom, presentation suites, and lecture halls, where the operation of the large number of devices that define the room function would make manual operation of the room very complex. It is common for room automation systems to employ a touch screen as the primary way of controlling each operation. See also, control engineering, control system, digital home, home automation, HVAC control system, lighting control system, list of home automation topics, smart environment, testing adjusting balancing, HVAC. Protocols and industry standards ASHRAE is an international organization for people involved in heating, ventilation, air conditioning, or refrigeration. BACnet is a network communications protocol for building automation and control systems that has been adopted worldwide as ISO 16484-5 2003. SBUS, Chartered Institution of Building Services Engineers, DINET, Energy Star is program created by the United States government to promote energy-efficient consumer products. NOtion, KNX, a system for home and building controls. DALI, network-based systems that control lighting in buildings. LONTalk is a protocol created by Echelon Corporation for networking devices. The official ISO standard numbers for building automation worldwide are ISO IEC 14908-1, ISO IEC 14908-2, ISO IEC 14908-3, and ISO IEC 14908-4. MIDAC, OPC is an industry standard used widely in manufacturing, process control, and building automation. The open standard transfers, values, historical data, and alarms and events. OpenTherm, OpenWebNet, VSCP, Zigbee is a short-range, low-powered wireless communications standard targeted at building automation. References. External links. Wikiversity, Building Automation provides learning resources for professionals in this area. Key elements in intelligent buildings, European Building Automation and Controls Association, UBAC.